Hello everyone, myself N. Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous session, we discussed about unsymmetrical bending of beams and in which we have seen what is the formula for direct stress distribution due to unsymmetrical bending, that is the formula for sigma z, and also we have seen the position of neutral axis, that is tan alpha. Let's try to use that the formula which we derived in the previous session, and let's try to look into few problems in this module. So moving on to this, problems on direct stress distribution, the learning outcomes, students are able to solve problems on unsymmetrical bending, and they are going to determine the direct stress distribution for various cross sections. And the first problem which we see here is this one, which is nothing but the T section, and it is an unsymmetrical section again. This is neither symmetrical about x-axis nor about y-axis, and you can see the dimensions that are given. And what is the question we are having here is a beam having the cross section that is shown in figure is subjected to a bending moment of 1500 Newton meter in a vertical plane, and is asking to calculate the maximum direct stress due to bending, stating the point at which it acts. Okay. So you are going to find out the maximum direct stress, that is sigma z max, that we need to calculate. Okay, and after that we need to calculate at what point you are going to get this maximum stress. Okay, so before we go into this problem, let's look into the formula. So the well-known formula for this nothing but my into ixx minus mx into ixy divided by ixx iyy minus I square xy into x plus mx iyy minus my ixy divided by ixx iyy into I square xy of y. We should not forget that. Okay. So this is the formula for direct stress distribution which we have derived in the previous session. So this formula we need to use. Okay. So before we proceed for this problem, let's look into this one and what is there in this and what we need to calculate. Okay. So if you look into this one, first of all, we need to understand that the first point, it is an unsymmetrical section. So since it is an unsymmetrical section, even we need to calculate the product of inertia also, it is not going to be 0. So we need to calculate the moment of inertia about x-axis, and we need to calculate the moment of inertia about y-axis, followed by the product of inertia, that is ixy. So 3 moments of inertia we need to calculate. So we know that if you want to calculate the moment of inertia, we should know the position of centroid, and in the diagram the position of centroid is shown here, but you need to calculate it properly. And the position of centroid, that C, is nothing but x bar y bar, and for that you have the formula for x bar, that is equals to, you can write a1 x1 plus a2 x2 divided by a1 plus a2, and for calculating the position of y, you can write the formula a1 y1 plus a2 y2 divided by a1 plus a2, and you can do that by dividing this T section into 2 rectangles, and you can divide into 2 rectangles, and you can consider this as first rectangle, and you can consider this as second rectangle. And then after dividing into 2 rectangles, let's try to look at its centroid, local centroid. So the local centroid may be here, you can write it as G1, and for the second rectangle the local centroid may be here, you can mark it as G2, and where C is the total figure centroid. Small g1 and small g2 are the local figure centroids, that is for A, B, C, D, the centroid is g1. For you can write this as gh. So for G, H, F, E, the centroid is g2, that is a local centroid, and it's very, so if you denote like this, it is very much easy for us to find the distances of x1, x2, y1, y2, and so that you can put it into this x bar and y bar equations, and then you'll get the position of centroid. Once you get position of centroid, and later you can move on to the finding the moments of inertia, that is ixx, iyy and ixy. So this is a story about this ixx, iyy and ixy, and Apart from this, in this equation, what are there is my, mx. Okay, everywhere in this here also mx, my here. But in the question which we've seen here, he just mentioned it is subjected to a bending moment of 1500 Newton meter. He is not mentioned whether he has given mx or my, but he is just mentioned bending moment of 1500 Newton meter. But he mentioned that it is applied in a vertical plane. So the bending moment which is applied in a vertical plane, which is nothing but it is nothing but the mx. So which is given as 1500 Newton meter, which you can convert into mm by multiplying 1000. So that is 1500 into 10 cube and Newton mm. So this is the bending moment applied in vertical plane that is given to you, that is mx. And the other one my, which is not given, you can assume it as 0. So when you substitute my equal to 0, and the formula will slightly reduce, but the product of inertia is not 0. That you need to calculate. Okay, so that's the procedure what we do here. First we need to find out the position of centroid, and then you need to calculate the moments of inertias ixx, iyy and ixy, and after that you are going to substitute in the equation for sigma z. So let us assume this equation as first equation. Okay, and after that you substitute all the equations in that, you are going to get the direct stress distribution. And once you get the distribution, and you can find out the point at which you are going to get the maximum bending stress by iterating the position of A, B, C, D, E, F according to the coordinates from the centroid position. Okay, so let's look into this problem. So as I mentioned, the position of centroid first may be calculated. So here the x bar, y bar. So if you look at into this here areas. Okay, so first area A1, you can, this nothing but 40 plus 80, that is 120 mm, and the depth is 8 mm. So therefore area is taken as A1 is taken as 120 into 8. Okay, and if you look at the second area from here to here, that is 80 mm into 8, that is the second area. So 80 mm into 8. And similarly, if you try to write the x distances also, so x1 is from the distance from here to here. So total distance is 120 mm, and half of the distance will be 60 mm. So x1 will be 60 mm. x1 equals to 60 mm, and x2, if you try to look from the diagram, so again you are going to take the same reference point here, and but you are going to take up to the second figure centroid, that is here, which is nothing but the same distance here, this one, that is 40 mm. So x2 you are going to get 40 mm. Similarly, and what is required here is y1, y2. So let's try to write y1 also here, y1 and y2 also here. So y1, and for that measuring y1, you can consider this topmost axis as reference line. Y1 is from here to here, the distance here to here, so which is nothing but half of the distance, that is 4 mm. And y2 again from here to the center of the second figure. Okay, so this you can consider, and 8 mm plus half of this 80 mm. So 8 plus 40, that is 48 mm. So here it is 48 mm, and here it is 4 mm, that is y1, y2. So you can write that value, y1 is 4 mm and y2 is 48 mm. So by taking these values of a1, a2, x1, x2, y1, y2, and you can substitute in the formulas for x bar and y bar, and when you try to substitute this, you are going to get y bar as 21.6 mm, and you are going to get x bar as 16 mm. So once you get the position of these x bar and y bar, you have to substitute, you have to denote the centroid position in the diagram. So already the centroid position is denoted in the centroid, that is here. So that is nothing but what, from this one. Okay, so that is the centroid position what we got, 21.6 and 16 mm, right? So after that, once you get this centroid position, then we'll move on to ixx. And now here the formula for ixx. So ixx can be written as, and here we have divided into two components, and you can write this as ixx for the first figure and ixx for the second figure. And usually the general formula for ixx is nothing but Ig, that is the moment of inertia about its own centroid, plus A into y bar square, that you have to remember. Okay, so that you are applying here. Since there are two components, let's try to write this as Ig1 plus A1 into y1 bar square plus Ig2 plus A2 into y2 bar square, that is Ixx. Okay, moment of inertia about x-axis. So you have to find out for the two rectangles. One is this rectangle and one is another rectangle. So Ig1 is the moment of inertia about its own centroid. By applying A into y bar square, you are shifting the moment of inertia to the centroid of the figure. So you are going to get moment of inertia about this axis. Okay. So if you try to look at this one, and Ig1, which is nothing but 120 into 8 cube by 12 into area 120 into 8 into y1 bar square, that is 17.6 y1 bar. So from the diagram, it's very important here to note what is y1 bar, what is y2 bar, what is x1 bar, what is x2 bar. So if you know this one, you can substitute directly in the formula, and Ig1 is nothing but BD cube by 12, and you can take for the first diagram B1 D1 cube by 12. Here Ig2 is nothing but a B2 D2 cube by 12. Okay, and correspondingly A1 is nothing but B1 into D1, A2 is nothing but B2 into D2. So from the diagram, if you try to understand, okay, so y1 bar from here to here, that will be y1 bar. So total depth what we got here, it is 21.6, and from here to here it is 21.6. You have to subtract this. So y1 bar is nothing but the distance from first figure centroid to the total figure centroid, the vertical distance, y1 bar. Okay, and y2 bar means again the distance from second figure centroid to the total figure centroid, vertical distance, that is y2 bar. Okay, and x1 bar, the distance between horizontal distance between total figure centroid and first figure centroid, this is x1 bar. Okay, and x2 bar is nothing but the distance between horizontal distance between second figure centroid and the total figure centroid, that is x2 bar. Okay, so just you need to understand that y1 bar is nothing but the distance from first figure centroid, horizontal vertical distance between first figure centroid to the total figure centroid. So that is CG1 vertical distance, and y2 is again CG2, distance between C and G2, again it is a vertical distance, and x1 bar is the horizontal distance between C and G1, that is a horizontal distance, and x2 bar is the horizontal distance between centroid, total figure centroid and second figure centroid. So in this way you can clearly note down the values from the y1 bar, y2 bar, x1 bar, x2 bar, and you can substitute. So here in this place you get y1 bar, and here you are going to get y2 bar. So the second figure again b into d2 cube by 12 plus area 80 into 8 into y2 bar square, that is 26.4 square. Okay, and when you try to calculate this, you are going to get Ixx, that is equals to 1.09 into 10 to the power of 6 mm power 4. Okay, similarly Iyy also can be calculated by using the similar formula, except that here slightly you are going to get changes here. Same you are going to find out Iyy, that is equals to Iyy1, Iyy2, and here also you are going to get Ig1, but instead of A1 y1 bar square, you are going to get A2 y2 bar square. So in this, if you try to replace this by x1 bar square, and this you are going to get Iyy, and here instead of this b1 d1 cube by 12, you are going to get b1 cube d1 by 12. Similarly here also the cubes will interchange, and then instead of y2 bar square, you are going to write x2 bar square. So that is the formula for Iyy, and here Iyy equals to Iyy1 plus Iyy2, and you are going to get the formula, similar formula you can apply. So you know already all the dimensions b1 d1, you know y1 bar, y2 bar, x1 bar, x2 bar, You can substitute in the formula and you can get Iyy. Okay, that is the second one. Third one is Ixy. So Ixy formula is nothing but simply A1 x1 bar square y1 bar square plus A2 x2 bar square y2 bar square. So you know already A1 A2 from the diagram, and you already know x1 bar x2 bar y1 bar y2 bar from the diagram geometry of the figure, and you can substitute. You are going to get the moments of inertia Ixx, Iyy and Ixy. So I hope these moments of inertia are not that tough, because this kind of moment of inertia you already done in engineering mechanics subject, and you already done in this mechanics of solids or strength of material subject. So these are basic moment of inertia what we are calculating here. So once the moments of inertia are calculated, almost all the problem is over, and after all which is left is nothing but only the substitution in the formula for direct stress. So next, so we know that formula sigma z, that is equals to my Ixx minus mx Ixy divided by Ixx Iyy minus I square xy into x plus mx Iyy minus my Ixy divided by Ixx Iyy minus I square xy into y, in which my from the given condition, that is 0, and you can substitute for mx 1500 into 10 cube, and here also you can substitute 1500 into 10 cube, and Ixx Iyy values you can substitute, and when you substitute and try to reduce the form, you are going to get sigma z equal to 1.5 into y minus 0.39 into x. Okay, so this is nothing but the distribution, direct stress distribution we got in terms of x and y. Direct stress distribution. Once you get the distribution, and he asked to calculate the maximum direct stress, sigma max. So you need to iterate because you have got different points A, B, C, D, E, F you have. Okay, at what point you are going to get the maximum direct stress means you need to iterate. You have to write the coordinates of A, you need to write the coordinates of B, C, D, similarly coordinates of E, F, like that you have to write. Okay, so for each and every point you need to write the x coordinate and y coordinate, and then you have to substitute in this distribution for sigma z, you will get some value. So like that you have to iterate for all the values, and you get only one value, that is will be maximum. For example, if you try to write the coordinates for point A, let's look into the diagram, try to write the coordinates for point A. So point A is this one and centroid is this one. So point A, its x axis, so that is x axis from here to here, x coordinate from here to here, and which is usually minus you're going to get. Okay, so A coordinate is, again from the diagram you can see clearly it is minus 40, and its y coordinate is above here, that is 21.6. Okay, and now this take this x coordinate, A point coordinates, and substitute in the formula for sigma z, you are going to get sigma z A. Similarly, if you try to look at point B, and so it is not this 40 only, the distance you have to measure from here to here, x bar, whatever you got x bar, that you have to write here, x bar. Okay, similarly you have to get the coordinates for point B, point C with respect to the centroid, point F and point E. You have to inspect, you have to find that coordinates and substitute in sigma z accordingly, so you will get stress at that point. Then only you can able to tell at which point you are going to get the maximum stress. So from the analysis what we got here, stress will be maximum at point F, where its x will be minus 8 and y will be minus 66.4 mm, and you are going to get, when you substitute in that equation, you are going to get maximum direct stress, that is equals to minus 96 Newton per mm square, which is a compressive stress, but still it is maximum stress. So this is the way how we find out the formulas, find out direct stress distribution due to unsymmetrical bending, that is sigma z, due to unsymmetrical bending, that is mx and my. Okay, so that's all for today's session, and in the next class we have some more problems, or the additional, that is the moment of inertia which we have seen here, and this is a normal moment of inertia. So in the next session we look into the problems in which we'll have some thin wall approximations, and followed by moment of inertia of inclined section. Thank you everyone.